welcome everybody. I think we should go ahead and get started. Our president is here, and I am Lisa Stewart. I'm the Chief Administrative Officer at the Kavli Institute for Theoretical Physics. We are thrilled to restart this fabulous series, the Innovate seminar series with NSBP, the National Society of Black Physicists, and to welcome our new leadership team to this event. And I am going to stop right there. Just thank you for being a part of this event today, all of you on the panel and on the guest list, and turn it over to Elon Price, who will give us our next steps.
Okay, can everybody hear me well? All right, dope. So hello, everybody. Happy Thursday and happy equinox. Just found that out. My name is Elon Price. I am the student representative for the National Society of Black Physicists. I'm also a physics PhD candidate at Auburn University. And I don't know about you guys, but I am pumped that we get to restart this series and continue to hold a space for our membership to come and to shine with their really dope physics research. So with that, I'd like to also mention that anytime during this talk, even though it's not as interactive as a regular Zoom, we do have a webinar format, but anytime you come up with a question, please add it to the Q&A section of the chat, and we will have a Q&A session at the end to address all of those questions that come up during the talk. And to moderate that session, I have with me another student council member. By the way, we are 10 strong, but today we have student council member Carlton Smith to be our Q&A moderator. So with that, I'm going to turn it over to the president of the National Society of Black Physicists, Dr. Hakeem Oluseyi.
Hello there. Thank you very much, Elon. And it was not lost on me that she introduced herself as a PhD candidate. Congratulations. You passed her qualifying exams. And you know how important that is. I am absolutely proud and honored to be able to participate in this particular production. This is a joint effort between KITP in Santa Barbara, right, Kavli Institute, and the National Society of Black Physicists. I am the newest president of the National Society of Black Physicists. We have a very active and very impressive student council. Elon is the leader. She's the rep to the board of the National Society of Black Physicists. But my job here today is to introduce our speaker. And Christian, sir, you may not realize this, but we're sort of cousins because I too have worked in galactic archaeology. But, you know, being not as smart as you, I use RR Lyrae stars, which are nowhere near as numerous as the type that you use. And, you know, with the James Webb Space Telescope and the Vera Rubin telescope coming down, I know that you're about to like just map out our entire galaxy and figure out how this whole thing was made. So I'm incredibly excited about it. So for a proper introduction, Christian is a final year graduate student. How do you figure that, Christian? Are you sure it's the final year? Have you started writing? You know, I had like 2 or 3 final years, but anyway, and he's a graduate of Morehouse College, the very famous, very distinguished Morehouse College in Atlanta, Georgia. He studies the properties of low mass stars and brown dwarfs and how they can be leveraged to understand the formation and the history of our Milky Way galaxy. He's also interested in detecting gaps in globular cluster streams as potential avenues for testing dark matter models. He is a recent winner of the NSBP Beth Brown Memorial Award. And so I just have to say this, you know, Beth Brown and I were the only 2 African-American astronomers who graduated from HBCUs. I graduated from Tougaloo College. She graduated from Harvard, who went on to actually have research careers in physics. And in fact, in astrophysics. And in fact, you know, the joke among all of the Black astronomers of America is that Hakeem, me, is the only guy who you can tell is Black on the phone. but I absolutely love Beth Brown, and congratulations, Christian, because Beth was she's definitely one of those people that no one could have anything bad to say about her, right? I mean, she was that good of a human being in addition to being an amazing scientist. So with no further ado, I turn it over to soon to be Dr. Aganze.
Thank you so much, Hakeem, for a really nice introduction. Let me share my slides. All right, thank you for a really nice introduction. My name again is Christian Aganze. I am a graduate student, a final year graduate student at UC San Diego. And this talk is going to be about galactic archaeology with ultracool dwarfs. And in the background here, you see a really nice artist illustration of what those ultracool dwarfs are. Ultracool dwarfs are basically a funny way of saying low mass stars and brown dwarfs. So a little bit of my outline, I'm going to talk a little bit about galactic archaeology and ultracool dwarfs and why we should study galactic archaeology with ultracool dwarfs. And then I'm going to talk about one of my papers on finding ultracool dwarfs in deep HST surveys. Then I'm going to talk about how we use these samples to actually map out the galaxy. And then I'm going to again look ahead and say what the JWST telescope, Rubin, and all these upcoming telescopes are going to do for us in these fields. But I want to orient you in a sense on what the science questions are before we actually start diving into these questions. So some of the questions that we can ask are the chemical compositions of halo ultracool dwarfs consistent with what's in FGK stars? And then is the number fraction between the halo and the disk similar to what we see with main sequence FGK stars? And then we want to know what drives kinematic heating in the disk, and that is change with low mass stars. What's the effect of metallicity on the hydrogen and burning mass, and also the minimum mass also, but also the smallest thing that it can form. And are we sitting in a really strange 100 parsec neighborhood that we're seeing all these phenomena ultracool dwarfs in? So if these questions don't make any sense to you, don't worry, I will come back to them. Just to orient you, ultracool dwarfs again are these low mass stars and brown dwarfs. So you can think of them in terms of mass, so things below 0.1 solar masses, and they're also the bottom end of the mass function. So the fraction of stars per mass, and that makes them around 20% of all the stars in the universe. And this is a nice cartoon illustration of that. So you have the so-called M dwarfs, and we're going to be using these letters M, L, T, and Y. So these are spectrotypes, and they're roughly temperature ranges. So M dwarfs are around 3,500 Kelvin, L dwarfs are around 2,200 Kelvin, and then T dwarfs and Y dwarfs are things below 1,000 Kelvin. And then you have Jupiter that's sitting there. This is a planet, but we just put it there for comparison. And the size of this object is almost identical to Jupiter. That's just how the physics works out. And so if you just look at this object and how they evolve with time, so here I'm plotting evolutionary models. So on the x-axis, I'm showing the logarithmic age in billion years, and then the temperature of the object. And then each one of these lines is a model of the mass of the evolution of an object with a given mass. And the mass go from very high mass, so 0.1, and then to really low mass, almost to Jupiter-sized mass. So brown dwarfs will be the things that are cooling down with time because this object don't fuse hydrogen in their core. And then stars are this object that just contract and they stay the same temperature because they're probably fusing deuterium and probably hydrogen. And then the planets here, I put this label here for planets, but these are actually ultracool dwarfs, but ultracool dwarfs in these temperature ranges seems to have the same atmosphere as planets. Again, these are models. When you look at their spectra, the actual data, you see that the spectra peak in the infrared, so around 1 micron. And then we have this really strange chemistry in the atmosphere. So this plot here is a stack of spectra. So on the x-axis, I'm showing the wavelength. And then on the y-axis, I'm showing the flux that's coming from this object. Again, it peaks at around 1 micron, and that's the infrared region of the spectrum, of the electromagnetic spectrum. And so the top spectrum here is the NEM dwarf, which is really dominated by water and the other features. And then you have L dwarfs that have a lot of carbon in them, CO. They still have a lot of water, And then you have the T-dwarf spectrum, which is mostly dominated by methane and these really deep features. And then I'm also showing Jupiter for comparison. Again, these objects are really interesting, just chemistry-wise. And they're very common in the local neighborhood. So if you look within the 10 parsec, this is a compilation of the 10 parsec sample by Rayleigh et al. 2021. And the x-axis, I'm showing the spectral type of the object, and the y-axis, I'm showing the number of stars. And the arrow is indicating where Ultracool dwarfs seem to lie. So you can see that it's really the majority of the stars at least in the 10 parsec, at least in a huge fraction, depending on where you cut out the Ultracool dwarfs to be. But the problem is we only see them locally because they're so faint. So what I'm showing here is what we call the luminosity function. So the number of stars per volume, per temperature range, that's what's plotted on the y-axis. And on the x-axis, I'm showing the distribution of temperatures. So the temperature and the distribution of these objects are shown by these measurements that are just points, and then we fit models to this. Depending on some assumption about the mass function, you see that the low mass end or the low temperature end is not really well constrained, but the rest of we understand the evolution of the rest of the object pretty well, except when you get to low temperatures, we really don't know the minimum. This is really sensitive to the minimum object that can form. And that's in itself, it's actually a research science question that we should care about. What's the smallest thing that can form as a brown dwarf? But the galaxy itself is much larger than the 100 parsec range, right? So this is what I'm showing here is a cartoon version of what the galaxy looks like. So we sit around this area here, around the sun, and you can imagine 100 parsec is a much smaller volume compared to this 8 kiloparsec from the galactic center. And then we'll sit in this so-called thin disk, mostly populated with metal-rich, relatively young stars, and then as you move away from that, you go up, you see what we call the thick disk. And then at the center of the galaxy, we have the bulge, which has a black hole. And then outside this one, we call the stellar halo. So these are really old stars that are moving in very strange orbits. And then we can also see some satellites of the Milky Way, some globular clusters. And then all these things sit inside what we call a dark halo, some kind of dark matter potential. If you look closer in the halo, and this is something that has been revealed by Gaia, is that if you plot just, in this case, I'm showing the distribution of velocities of stars in the Milky Way. This is centered around the sun is around 200 kilometers per second, roughly. So I'm showing on the x-axis, I'm showing the Vy, and then on the y-axis, I'm showing the rest of the velocity components. What we learned from this is that most of the thin disk stars move around, move through the galactic rotation. So that's what this prograde means. And then once you start moving away from this thin disk, you get the halo and the thick disk. And we believe that the halo was actually formed from this Gaia Enceladus blob, which is really some kind of satellite galaxy that merged with our own galaxy and created this really interesting population. And that also heated the disk and created this hot, thick disk part of the galaxy. You can also see that in metallicity space. So if you plot a fraction of iron that are in these stars, and this is again a plot from Micro 2019, and then on the x-axis we're showing the fraction of iron. This is an algorithmic space, so how much iron there is compared to the sun, and you put that in log space. And then on the y-axis, how much magnesium. Magnesium is interesting because it's an alpha element. And so you see different populations chemically. And this is colored by the eccentricity of the object as it moves around the galactic potential. So halo stars seems to be this alpha enhanced, so they have more magnesium than thin disk stars because they formed at an earlier epoch in the Milky Way when they were not really polluted by epochs of star formation. And this is also true for some high alpha elements of the disk. The problem is all of this is we learn a lot about the galaxy by just looking at FGK stars, and we haven't actually explored what Ultracool dwarfs will give us in terms of this picture. This is because Ultracool dwarfs are rare, right? They're very faint, they're extremely faint, so we can only see them locally. But sometimes we get one of these halo stars that's moving really fast that come across the solar neighborhood, and we can actually map its orbit. So this is an example of one of those objects. This is STHS J1256-0224. That's a long name for the object. And this, what I'm showing on the x-axis is the radius in galactic coordinates, and then this is cylindrical coordinates, so R versus Z. And then there's a cartoon version of the disk, and then the bulge of the Milky Way. And this is kind of tracing its orbits. And then the dark color, the dark points here are its future orbits, and then the dashed ones are the previous orbit. You can see that this object goes all the way up to 10 kpc above the galactic plane. And people have been able to also confirm the metallicity of this object. It's really metal poor. It's 10 to the minus, almost 10 to the minus 2. It has less iron than the sun to a factor of 10 to the minus 2, and it's moving at a radial velocity of 130 kilometers per second. But again, these objects are really rare. We don't see them a lot. Also, one thing we've learned about the Milky Way brown dwarfs is that they're highly dispersed. So this is an example of I'm showing what those velocities are. So these are velocities again, but not in Cartesian space in this other coordinate system. So the yellow points are the L dwarfs, and then the white points are M dwarfs. These objects are in the local neighborhood are really dispersed. So they go up to almost a thick disk. And previous studies have shown that actually, if you run a simulation, you find that the fraction of thick disk L dwarf is actually was underestimated by previous surveys. So we know all this stuff about the Milky Way, we know all this stuff about ultracool dwarfs. Why actually try to link the two? Why study ultracool dwarfs with the Milky Way? Again, which brings me back to my science question. We want to actually understand if the halo composition is the same. So what is the fraction of halo stars that are FGK stars versus halo stars that are ultracool dwarfs? What drives kinematic heating in the disk? Why L dwarfs so highly dispersed compared to M dwarfs, or at least compared to T dwarfs? And then does the metallicity affect the hydrogen burning mass? Like if you move in the halo, you get a different composition. How does this affect this, not only the hydrogen burning limit, but the smallest thing that can form? So all these questions, again, go back to why we should start actually looking at ultracool dwarfs in the galactic context. So to do that, we actually have to find distant ultracool dwarfs. So which brings me to my first study that I did. So ultracool dwarfs are really local, but to find the ones that are really distant, you have to use deep imaging surveys like the HST telescope, which was used by Ryan Jr. in 2005, where they discovered 28 LNT dwarfs in 15 fields. And here I'm showing what we call a color magnitude plot. So on the x-axis, it's the difference in magnitude between two bands, and then on the y-axis is the magnitude. And they were able to select brown dwarfs, but again, the problem with this study is they didn't have enough color information to actually tell the spectrotype. Therefore, they couldn't actually constrain their distances. If you look at use other cameras that have spectroscopy, you'll find that. So if you look at spectroscopy, the spectroscopic samples are really limited in the number of stars, brown dwarfs that they can show us. So in this case, I'm showing a study by Masters et al., where they only found 3 T dwarfs in the different surveys. So the goal of this survey was to actually go further and find more of this spectroscopically confirmed again, so we can measure the distances of these objects. We need to know their spectroscopy, the spectrotype. So for that, we use the survey called WISPS and 3D HST. These are 2 surveys that are being run again by different teams, but the goal is to actually look for high redshift galaxies, and they look at different high galactic latitude fields. So this is what I'm plotting on this map here. Is a map of the sky where these pointings are. They're looking for high redshift galaxies, so they have to look up, and then occasionally they get contaminated with brown dwarfs that are in the Milky Way. So we can actually go into that data and find all the brown dwarfs. A study found that, again, they were looking for high redshift galaxies, and they had a lot of brown dwarfs in the background, but they were not able to find all those brown dwarfs. So my job was to actually go into the data, which looks like this. So if you just take in one pointing of the survey, you will get a bunch of stars in there and galaxies, and then you can take this an image at 1.6 micron. That's what that F160 stands for. And then if you take a spectrum of that, you get a spectrum of every object in the field. The problem is the overlap, but the people have figured out nice algorithms. It just the 1D spectrum extracted from these images. And to find brown dwarfs, I actually need to have a known sample of brown dwarfs that I can work with. So I start with a library called the SPECS Prism library. So these are data taken by the SPECS instrument on the NASA Infrared Telescope. And switch float I'm plotting here. Again, these are spectra. So on the x-axis, I'm showing the wavelength. On the y-axis, I'm showing the flux. And these are different standards. So this is what a typical M7 will look like. This is what a typical L0 will look like. And then I select region in the spectrum, which is all these gray lines are, where we can actually probe the sensitivity to water and methane in this feature. So I measure what we call an index, which is the ratio of fluxes between different parts of the spectrum. So if you plot those indices against each other, you will find that galaxies and point sources usually cluster around some point, and there will be some spread. But if you plot brown dwarfs, they'll actually follow some kind of trend, because these objects have different level of sensitivity to water and methane in the atmosphere. So you can actually select them. The problem is, the good thing is you can select them. So this is what those stars are, the selected objects. But occasionally you will get other object, and this other object that you get are actually selected by another method, which is machine learning. So again, this selection, just to reiterate that, this selection is not as accurate because again, you see objects that are not quite the exact spectral index that you expect. Again, these are rigid boxes, so you need to actually go beyond that. So we use machine learning. In this case, I'm just going to explain exactly what machine learning is briefly. So in this case, we're using supervised machine learning. In the simplest case, you have a bunch of pictures of cats and dogs. You label this picture cat, you label the dog picture dog, and then you feed the data into some kind of machine, and then the machine will tell you, if you give it a new image, the machine will be able to label those images correctly. So I've been training undergrads to actually do this, and also some high school students to actually do this, to actually do other stuff like photometric classification of stars and finding new binaries. And some of them have written research notes that you can check out. But for my case, I used this to find brown dwarfs in this field. So we looked at a training set of 3,000 known brown dwarfs in the library that we have here. And we looked at all the objects that are flagged as galaxies in this survey, so 150,000. And then we predicted for everything that's a point source, everything basically that's not a galaxy. And then we measured the same values like spectral indices. We also add some other features like the signal to noise of the spectra and other comparison statistics. So we use two methods. One of these is the random forest method. And briefly, what this method does is splits the data into different sets. So we start with the data, and then we can split into value that are greater than 1 or value that are less than 1. So you always do this binary tree splitting. And then in the end, the final classification will be measured by the majority vote between all these decision trees. And then you can actually train them to optimize some criteria. We also applied a neural net. A neural net is, briefly again, it's a bunch of transformation between input and output. So this input layer here will be, we'll put the data, and then each one of these dots is a transformation to the data until we get into the final output, which would be, is this a brown dwarf or is this a galaxy? And we usually use numbers, and then we can actually optimize some criteria to some error metric. The result of this method is that with indices, again, here I'm just showing the table of how many objects I was able to discover with these methods. It looks like the indices discovered the same amount as neural net and random forest, but the indices were really contaminated. So we had a lot of objects that we didn't need. In this case, we had 3,400 extra objects that we actually don't need, compared to 120, which were much lower. So we get really a high contamination if we just use indices. Here's some examples of those discovered objects. So here you can see we discovered total of 164 M7 to M9, and then 26 L dwarfs, and then T dwarfs and then this distances are up to 10 kpc. Sorry, not 10 kpc, but 1 kpc for M dwarfs, and then half a kpc for T dwarfs. And then you can actually plot the spatial distribution of these objects. So on the x-axis, I'm showing the galactic coordinates. In this case, radius versus galactic height, and also just plotting the distribution of those. You can see that we get actually in the 2 kpc and then above 1 kpc. So this is really interesting. We're going to start probing this deep. Again, the goal is to actually start probing this deep field and see if we can actually detect objects that are actually not just in the thin disk. We can actually see objects in the thick disk in the halo. But we were not able to find any clear halo or thick disk sources from just looking at the spectra. So from this, we actually measured what we call galactic structure. And I'm going to explain exactly how we did that. So we use this framework of Monte-Carlo simulations. Briefly, this takes a bunch of inputs, and then we do some transformation of those inputs. So we know something about the mass function, the star formation history. We know how this object evolved, and we can put all that stuff into a ball, and then in the end, we get how many objects we should get in this survey, and what's their magnitude distribution, what's the spectral type distribution. We are able to scale that to the luminosity function, so we know how many objects are local, so we can actually have a way to calibrate this Monte Carlo simulation. So this is what I'm showing here, and we're able to reproduce those numbers pretty well. And so again, this is the same plot I showed from the Kirkpatrick 2021 paper, where they just measured what's the volume density of object within 20 parsec. And then once we scale it to the local sample, remember that Ultracool cool with time. So as you look in all the population, object will cool down, so they will pile up at low temperature ranges, which is what this plot is showing. So as you increase in age, the evolution tends to go to cold objects. So you get lots more of cold object compared to hot objects. But again, this also depends on the actual volume that you're looking through. And the volume will depend on the intrinsic brightness of this object. So we can actually infer what we call scale height, and it's a parameter that measures basically the amount of exponential fall off in the density of these objects. So on the x-axis, I'm showing the subtype range. We didn't have a lot of objects, so we grouped them in subtype range instead of doing every spectral type separately. And then on the y-axis, I'm showing the number of objects that we detected. And each one of these lines is a prediction from a model that involves Ultracool cooling and what we know about galactic structure. Basically, this density law here, which has this parameter called scale height h. And each one of these dots so the open dots are objects that are outside what we call our magnitude limit, and then the solid ones are the objects that are inside our magnitude limit. And then with this, we can actually constrain the scale height of these objects. So we're able to constrain the scale heights like that, but we wanted to go further and go into what is the actual population age of this object. And in exponential disk, we can actually transform the scale height into a velocity dispersion, which was the first equation is showing. And then we can transform that velocity dispersion. In this case, it's in units of 20 kilometers per second for this scaling relation. But we can transform that velocity dispersion into an age using standard age velocity dispersion relations. And to get an intuition of why this happens is that stars that are older tend to be more dispersed in the Milky Way. There's so many models of why that's the case. One possible explanation is that as stars get older, they interact with spiral arms or other structures in the galaxy, so they get kinematically heated up and they have a higher dispersion in velocities. So what I'm showing in this plot on the x-axis is the type, and then on the y-axis, I'm showing the age. And the pink violin plots will be the inferred age versus the simulated age, and each one of these dots is the median. So we recovered the trend that the M dwarfs are older than L and T dwarfs, at least L dwarfs. We don't concern a lot about T dwarfs because we don't have large numbers of these. But we also confirmed that our simulated age roughly agree with our expectations. So to summarize this parallel survey work is that we discovered 164 ultracool dwarfs in these deep surveys. And for the first time, we were able to actually start seeing spectroscopically confirmed brown dwarf up to KPC scales. And then we're able to estimate the population age. We can't really estimate age of individual object, but we can estimate the age of the population. And we see that late M dwarfs are older than L and T dwarf, than L dwarfs at least. For T dwarfs, we have a huge scatter, a huge uncertainty because of the number counts. But we see that late M dwarfs are older, as expected from cooling models. And then for the next generation of surveys, we're going to actually just reuse the same method, again, the same Monte-Carlo simulation. So I'm going to just quickly go through this. So the idea is to take, again, this Monte-Carlo simulation framework where we input the mass function, the age, the cooling, evolution of these objects, and then we predict how many objects we will see with JWST. Can we constrain different models? Can we rule out some models? So looking ahead, it's really exciting. We're going to find, at least from these predictions, we're going to see for the first time in 100 halo dwarfs in some of these James Webb surveys, like the Passages survey, which has been awarded time. So what I'm showing here is the predicted surface density. So you can think of that number per area on the sky. And all of these lines are different predictions and different populations. But roughly, we will get around halo dwarfs. We get a lot of thin disk sources and a lot of thick disk sources, but we get around 100 halo dwarfs, which we actually start working with. Euclid will also be another mission by the Europeans, and this one will give us a little bit more halo dwarfs, around a few thousand, and they'll be in the deep field at least, because it's going to magnitude like 27, and it has also a much larger area. And then if we go to the Nancy Grace Roman telescope, it's going to give us a lot of thick disk objects, so around 10,000, and we can actually start understanding what drives kinematic heating in the disk. Finally, the Vera Rubin Observatory will also do the same kind of work, but with also precise astrometry. So we're actually able to measure the motion of this object as they move through the Milky Way. So I'm going to just, since I'm running out of time, I'm going to just leave you here with the comparison between different surveys. So JWST is going to be great because we're going to get the first confirmation of halo samples that are confirmed spectroscopically. So we actually see their the effect of metallicity in their spectra. And then with Euclid, Roman, and Rubin, we actually go to larger areas and we actually start understanding what happens with kinematic heating, what happens if you start actually looking at the minimum hydrogen burning limit, what is the fraction of disks to halo stars in the Milky Way. So again, bringing it back to these science questions. So I'm going to leave you here on my summary slide. Again, we find 164 objects in these surveys, and then we've confirmed that brown dwarfs that are late M dwarfs, at least, are older than L dwarfs. And then we're excited about the next generation of survey like Euclid, JWST, and so forth. These are going to really revolutionize how we actually study the Milky Way with these really tiny stars. I'm really excited about what these surveys are going to tell us about the Milky Way. Thank you.
Thank you so much, Christian, for your talk. It was really enlightening. It was a lot of exciting work, and I'm really excited to see the work you do with the future, in the future, with the opening or starting of some of these new surveys. So I'm going to give a brief introduction. I'm Carlton, for some of you who may not have met me before. I help run the Innovate seminar series, and I'm going to open the floor for questions. Just feel free to enter in any questions you have into the Q&A widget at the bottom of your screen, and I will relay them out to our speaker. And just again, want to say thank you to Christian once again for a really good talk.
Thank you.
So I had a question myself. I remember one of the tools you use to distinguish between the different dwarf, the different brown dwarf stars was first there was a, I believe it was a decision tree, and then later you used an artificial neural network. Is there necessarily like a reason for that you originally used the decision tree? And yeah, could you go over like the performance differences between the two methods?
Yeah. So that's a good question. So if I understand correctly, why did I choose those two methods instead of something else? Because so many machine learning methods.
Yeah.
Yeah. Honestly, I just landed on these two because they were the most popular, at least in astronomy literature. So random forests are great at, so let me go back to those slides. Yeah, so we use random forests, which is really combining different decisions trees together to make a prediction. Again, because they're just very popular in astronomy, and I've used them, and it's much easier to train on your. We don't use them on laptop, but if you want to do it on your laptop, you can do it. And then artificial neural nets, as you know, they're also extremely popular, so I also use them for that same reason. And then in terms of difference in performance, I think I have those slides here. So you can see this, what I'm showing you, it's called a confusion matrix, is how precise these methods can, differentiate between different classes of brown dwarfs and between brown dwarfs and contaminants. So this will be our metrics for the random forest. By the way, you can see just my screen without the chat on top of it. Okay, yeah. So what you see here is on the x-axis is the true label, whether this object was a contaminant, whether it was a named dwarf, whether it was a teal dwarf, an L dwarf, a T or a Y, or a subdwarf. And then the prediction, you can see that they match pretty well. And this is after doing some kind of parameter search. And this is also true for the neural net. It also performed almost the same way. Again, but they beat our traditional methods because they have a really low rate of contamination from external object, which is here. So you see the number of contaminants here that are not brown dwarfs is much lower if you use this machine learning method. So you get an advantage of using them. And then a bonus point, I got to train people to use them. So that was also, I guess, an additional benefit of using this method.
So thank you for answering my question. Really well answered. We have another question from actually Lisa. And the question was, she was, I guess, interested in hearing how you were able to engage high school students in, the research endeavor, and if you would be able to speak about your mentoring of, undergrads and high school students.
Yeah, so there's a program here at San Diego that's called the Enlace program that involves a lot of undergrads here, but also high school students from local high schools. We actually also have high school students from Mexico that actually come in at UC San Diego and work here. So they were, my experience with them has been incredible. They learn really fast and they were able to apply these methods. Again, they published 2 research notes. So they were able to do this really quickly and get feedback, and we were able to, again, we not only did we work on the research, but they also wrote a note. So they learn how to do scientific writing, how to present to conferences. So this is a great program for them. I didn't start the program. It's a UC, I think it's a UC-wide program that they've been participating in, but I was really lucky to work with them.
I have a question if no one else speaks up. Um, so a question for you. So since these objects are so cool, I imagine they have, here's the question. Can you see them on the other side of the galaxy with the JWST through the dust?
Right. Yeah, if I understand the question correctly, is they're intrinsically faint. We can only see them with Hubble, with KPC, and then how far can we see this object with JWST? And does dust
Well,
become a
well,
problem?
let me ask a little more. So so doing my work with our Lyrae stars, there
Mhm.
are giant cool stars that you can actually see on the opposite side of the galaxy in the infrared. And so these guys are much tinier and much less luminous. And so I'm just wondering if you're looking in the plane of the galaxy with
Mhm.
JWST, can you see them through the dust and can you map out, the galaxy in brown dwarfs? Galactic
Yeah.
structure. Yeah.
Unfortunately, if you're looking in the plane, you can't actually see them because again, dust is still there in the infrared anyway. So
Oh yeah, true.
you also get crowding from other sources.
Yeah.
So they're still, but if you look, how far are you going to see them with JWST? Um, the prediction here, I don't know if I don't have the number. I actually have the distances here. Yeah, so you can see that for M dwarfs, we can see them. So that's the axis on the top. So I have
Yeah.
I have a second one. We can see them
Ah,
roughly 3 kpc.
okay.
Um, and then but as you, again, this object is so faint that you only able, even with JWST, we're able to see them to maybe 10,
Oh,
and then for T-dwarfs, maybe a few kpc. We're still not looking on the other side of the galaxy. We're not seeing the entire disk, but we are probing a substantial fraction such that we can actually start making claims about kinematic heating in this, the fraction of this to halo stars.
well, the thing I'm wondering also is like, how different does galactic structure look if you just look at
Mhm.
these ultra cool dwarfs? Because I'm assuming they're not in the star forming regions, as much, and if they're older, then you'll get a different structure.
Yeah. So that's the question we don't have an answer to, right?
Yeah.
What does the galaxy look like if you just to look at it in Ultracool dwarfs?
Mm,
We know that they're not all old. We have some young ones, but L dwarfs cool down really quickly and become T dwarfs on a scale of a few of millions of years. So we actually don't know that. So that's why we measure the scale height. How far do they fall off exponentially?
right.
But we actually want to measure more than just that. We want to actually have the same richness in that we got from Gaia, for instance. I'm going to
Mm,
go back to that slide. We want to have this stuff, right? We want to have this uh,
yeah.
velocity structure. We want to have this metallicity structure. We want to understand any of this stuff, but we don't have any measurements because they're so faint.
Yeah.
But one reason why the galaxy might look different, right? Because again, one of the ideas about kinematic heating is it might be driven by object interacting with spiral arms and other structures in the galaxy. If that's the case, it's possible that it could depend on the mass of the object. And this very tiny object just get flung around in the Milky Way, and they're just on crazy orbits. Is that true? It's something we can test.
Excellent. Thank you, sir.
Yeah, thank you.
So we have another question in the chat, where the attendee asked, what's the reason for using ultracool dwarf stars for studying the architecture of an evolution of the Milky Way? They had a question of if it was mainly a question of like having a large sample of stars, or if there were like properties of ultracool dwarfs that you hope to use that gives you unique information not provided by other stars.
Yeah. That's a good question, right? So ultracool dwarfs, the question is why should we even bother, right, with these very tiny stars that are faint? We can see them far away. We will learn something new about the Milky Way, which again brings me back to these questions is we haven't looked, right? So we don't actually know, if they're gonna be different if you look them at large distances. Ultracool dwarfs cool down with time. So stars don't do that. Stars just stay the same temperature for billions of years. This cooling and evolution is really something that we haven't exploited. For instance, one possible avenue that's now being tested in globular cluster is Ultracool. Since they cool down, you actually see a gap in the main sequence stars and then brown dwarfs. If you look at a very old population like a globular cluster, you see that brown dwarfs are here because they all cool down, versus stars are here, and then there's a gap in the center because the entire population is old. And you can use this gap to actually trace the age of these globular clusters. And you can we do the same thing for the halo? Can we get a new halo age indicator, right? That could be something. And then we want to understand hydrogen burning, just the physics of it. Does this depend on the metallicity of the object? How high efficient this object burns of hydrogen? Remember, when we are looking at stars, we're not actually looking at the minimum mass of burning. We're looking at things that are burning hydrogen. We're not actually looking at this 0.1 or below 0.1 solar mass object that's where we start seeing the gap between hydrogen burning stars and non-hydrogen burning stars. The dependence of that on environment, we need to investigate that with ultracool dwarfs. So there are some reasons why we should actually try to understand this object in the Milky Way context. It's not just increasing the samples, it's also probing the science questions.
So this is a question of my own, and I think we'll close questions after this. Is there, I guess, and this may have been addressed in your talk, established theories for why you see that gap between stars and brown dwarfs that you were referring to?
Right. Unfortunately, I don't have a nice figure here for that. The gap between stars and brown dwarfs in all population is just an effect of cooling. If you just think of the color magnitude diagram, you have a color magnitude diagram, and then objects will cool down with time. Other objects are still burning hydrogen, so they become fainter. So they move down the luminosity, so that for the same color. There may be some change in color, but that cooling down, the other ones are burning hydrogen, so the other ones are cooling down, you get a gap at the center. So you don't need a new theory, but to understand the dependence of it on metallicity, people need to run models, and some people in our group are doing that, and other people are also exploring it.
Well, thank you so much, Christian, for both the talk and for very thoroughly answering all of the questions that all of us and the panelists had. So I'm going to pass the baton to Elon as she closes us out.
Thank you for your questions. Thank you.
All righty. Excellent. Excellent. I'm looking forward to linking with you, Christian, at the conference because I had a lot of questions, but I wanted to, hold the space. So thank you again for, coming here and presenting your work. Super, super cool research. And thank you everybody for attending. For those of you logged on and for those of you watching the recording maybe later, thank you so much to continue to support this seminar series. And with that, we're going to close out and see you next month.